Okay, now in this example, we want to design two encoders. Now, simple encoders can be designed as a regular logic function using the general method of the kernel map. This is what we are going to do in this exercise. If the encoder has many inputs, because you can have an encoder with 8 inputs, 16 inputs, or even more, then kernel maps are not right. And then you can approach the encoder design from a modular point of view, taking into account the characteristics of the encoder functionality. But in this exercise, we just use the generic method. So in the first case, we want to design a regular 4-bit natural binary encoder. In the encoder, the normal encoder outputs the number corresponding to the input that is active. So the table is like this, and we have lots of don't cares because the encoder is supposed never two inputs are active at the same time. So all the cases that are not in the table are don't care, as supposed to be don't cares. Okay. The other option for an encoder is to work as a priority encoder, where we avoid having don't cares. And this is the good option. Actually, it's not really good to have so many don't cares, because if something fails and more than one input is active at the same time, having a result that is not known, or that is some kind of random, may not be very good. So we normally prefer priority encoders that always have a deterministic output. But in this case, we are happy with a regular encoder. So we use the kernel map to specify our encoder. The encoder has two outputs that actually encodes the number of the active input. And we can start by specifying both outputs inside the map. So we have A1 and A0 together in the map. And now I will sort the variables here. Let's do like this: D3, D2, D1, D0. You can choose a different order, it's just the same. And now basically the interesting cases are where just one input is active. For example, here, only D2 is active. So if only D2 is active, the output should encode number 2, which is binary is 1, 0. Okay. Now this case is when two inputs are active, so it doesn't matter what happened. Okay, we don't consider that case, so we have don't cares here. Here, the active input is D3, so the output is number 3. No input active is something that we don't care, and so on and so forth. Here, this is D0, so the output is number 0. Here we have two active inputs, more active inputs, so we don't care what happened in all those cases. Like all these are don't cares. Actually, there are only 4 interesting cases. This is the remaining interesting case where D1 is active, the output is 1. All these are don't cares, right? Now we can to implement it using regular gates. We are going to move these variables to independent kernel maps. We may have done it right in one map, but I always prefer using repeating the kernel map. It may take a bit more time, but it's more clear, and it reduces the possibility of committing mistakes. Okay, so we have D3, D2, D1, D0. This is the map for A1. This is the map for A0. The same here, D3, D2, D1, D0. 1, 1, 1, 1, 0. So we have to be careful because we are going to have lots of don't cares. For example, for A1 we have don't care, 0, don't care, 0, don't care, don't care, don't care, 1. All these are don't cares, 1, and all these are don't cares. Okay. Okay, there we have 2 zeros, 2 ones. The map is quite symmetric, so it doesn't matter if we use sum of product or a product of sums. Okay, but first I will complete the other map. This is don't care, 0, don't care, 1, don't care, don't care, don't care, 0 here, don't care, don't care, don't care, don't care, and 1 here, and the same for this case. You see the map is symmetric as well. So let's go with the sum of product. We have this one here. This is a big prime implicant. To cover that one here. Now for this one, we have this big prime implicant. We don't have an adjacent one here. And that's it, because there are other options. For example, this one, this is a prime implicant as well. Okay, we may consider this, but this is of a smaller order than the ones we already have. Okay, and we don't really need to cover them, the don't cares. So it's not necessary to consider more prime implicants. This is what the remaining one that we may consider, but we see in advance that it's not necessary. And for the other one, this is a prime implicant as well. And for this one, this is don't know, maybe. Yeah, I may have to consider other options. Okay, I'll see now. Yes, if it's okay, we don't make any mistakes, then yes, this prime implicant may be interesting to consider, because with this prime implicant, we cover both mean terms at the same time. So it's the only one we need. We save some. We'll see. We'll try both solutions. Okay. The same in this case. We can use these two are prime implicants, but we also have this prime implicant here, the 4 corners in the map. Okay, it's another prime implicant. Okay, so possible solutions. We can select prime implicants 1 and 2, or we can select prime implicant number 3. Okay, for A1, in the first case, this prime implicant is simply D2. This other prime implicant is simply D3. That's it. Let's consider this case here. Okay, this is another option for A1. It's a different function, but it's also okay because it covers the mean terms. So in this case, this is D1 complemented. This is and D0 complemented. Okay. In that, for A0, it's a similar case. We have these two prime implicants, which is D3 plus D1, or the other option is to get the corners, the four corners. This is the implicant which is D2 complemented and D0 complemented. Okay. So what's the cost? Actually, if we evaluate the cost, here is the number of terms, which is 2 terms, plus the number of literals, but the literals are isolated. We don't count them, and we don't have complements. So the cost of this function is just 2 as the cost of this function. And the cost of this function is just 1 term. We only have 1 term here. And now we have to add the number of literals, but because it's 1 term, we don't really have to count, okay? Because to do just 1 term, we don't need an extra gate. So, but in any case, we have 2 plus 2 complements. So if we don't have variables in double rail, we'll need, our cost will be 4, okay? We need to, basically, we need an OR gate only, I need a AND gate with complements here, okay? Or if I do it, yes, I may try other options. Maybe I can, we can do it like D2 plus D3. If we have NAND gates, for example, we don't know the details because the program doesn't tell us to use some particular type of gate. So we can do it as we prefer or as we consider it is better. But it could be D2 complemented, D3 complemented and complemented, okay? This will be a NAND gate and 2 inverters, okay? So this cost will also be 4 in that case, in case we want to use NAND gates, which will be the most obvious or solution for that. We may also try with the product of sums and see all the combinations with and OR, only with OR, with NAND, and then try to evaluate the exact cost in gates. But anyway, we see our expressions are very similar. It's just 1 term, 1 term, 1 term, and 1 term. So any solution is good for us, okay? So if we just take the first one, if the problem says use only NAND gates, use only NOR gates, use AND and OR, then we will go for it, for a particular implementation. But now I will use that. And now that's it. This is very simple indeed. Now for A1, we'll have something like this. For A1, we'll have the 2 or the 3. This is an OR gate. And for A0, we'll have D3 or D1. And this is our encoder, okay? Now the problem says add an enabled signal after doing the design. We can do it as we did for the decoder, okay? And now the easiest way to do it, there are many options now for the enable. For example, we could add the enable using a gate at the output, okay? Something like I do an enable as by multiplying the full expression by the enable signal. The program doesn't say if we need to do it active high or active low, so I will select the best option. So to include an enable, we have to think on the gates as the functionality of pass-through gates. For example, if we have a NOR, we can add an enable signal in the NOR, in the NOR gate, because if it's like we have a active low enable, okay? If we have this is my enable signal, when E is equal to 0, it's like I enable my OR gate, because when E is equal to 0, this is an input that's like it does not exist. The result will depend on the rest of the inputs. But if the enable is equal to 1, then the output of the OR gate will be fixed to 1. Okay, so no matter what happened with the rest of the inputs. Okay, so a direct way to add an enable would be to it will be a active low enable. You can sign like this and connect it to both OR gates. Okay, that would be a simple option. Enable signals are often done like that. Okay, we do our regular design and then we add that signal as an extra signal to make it work in the regular way or not. When the enable is equal to 0, the enable bar is equal to 0, then the circuit comes is equivalent to the previous circuit. Or another option just could be if we want an active high enable, we may simply add a NAND gate at the output for both outputs here. Okay, it means introducing a new level in the circuit, and then this is an active high enable. Okay, now we use the characteristic of the AND gate. If the enable is 1, then the gate is enabled in the sense that the result will depend only on the rest of the inputs. Like this input does not exist. And if the enable is 0, then the output of the gate will be set to 0. Okay, so that's encoder. There is with an active high enable. Okay, these are the two options for the enable in this case. Okay. Now the problem also says to implement a 4-bit gray encoder. So what's that mean to if you want to do a gray code encoder? So the implementation is very similar. So let's clean up this a little bit. Let's move things around a little bit so we can draw everything in the same page. Okay, let's move it here. Let's move it here as well. So you have the options for the enable. So what's the difference now? I'm going to copy the previous solution. Because now we want to do it as a gray encoder. So the only thing is that if it's a gray encoder, the result we have to encode using gray code. Okay, we copy the gray code table here, but it's not really necessary because it is the output that we have to encode in gray. It means that for numbers, we have number 0, number 1, number 2, and number 3. Natural binary code is 0, 0, 0, 1, 1, 0, and 1, 1. But gray code, okay, this is N, this is binary, natural binary, and gray code for this is 0, 0, 0, 1, 1, 1, 1, 0. Okay, so the only thing that changes is that 0 is encoded like that, 1 is encoded like that, but 2 is not encoded like that. 2 is 1, 1, and 3 is 1, 0. So this is the only change in our design. Okay, so if we now consider the small maps, it's very similar to what we have already done. Okay, we may copy this. Great, so we will erase this one. So in this case, we take one of the signals, we remove the other cases, and now we can simplify that. Okay, that will be for A1, and we will simplify as we did before. If you see, I don't know if the same solution is good. Actually, yes, the same solution is good for A1, because in gray code A1 is the same than in binary. Okay, so actually I could have saved that. I will concentrate then in A0, which is the one changing, so we'll eliminate this. So I move the A0 now. This is 1, 0, 0, and 1. And now in this case, we could choose this prime impedance, this one together with this one. Okay. So the new value for A0 could be this, which is D2, plus this, which is D1. Okay. So A1 will be the same as before, which is D2 plus D3. In this case, we have D2 plus D1 instead of D3 plus D1. So basically the circuit is the same, but here instead of having D3 for A0, D3 plus E1, we'll have D2 plus D1. So we can actually copy the circuit, okay, including the we'll make it a bit smaller here. Let's make room for the circuit. Copy it. So if we copy the circuit here, now A1 is the same, and A0 will be D2 plus D1. Okay, so in this point here, we will have, instead of D3, we'll have D2 here. Okay, that's the only change, including this kind of enable. So as I said, this is the case of a simple encoder. The circuit is very simple because we have lots of don't cares, but in case that we have to design a priority encoder, it's a bit different, because in a priority encoder we don't have don't cares. Okay, my circuit is going to be much more complicated. And it's only for a very small 4-bit encoder. Okay? It can be more complicated. And there are techniques to design encoders of any number of bits, but it's something we are not going to see in this exercise. Okay, thank you, bye.